Swayam Prabha. Digital India. Educated India.
So you see, we are trying to understand torsion, okay, and trying to get a formula for that, all right. And so the torsion is defined just like the curvature first for unit speed curves, and then we need a formula which will we need a formula that will work for any curve, okay, not necessarily unit speed parametrized, okay. For a curve which is regular, not necessarily unit speed parametrized, there is a formula for curvature, okay. And then similarly, you want for such a curve, you want a formula for torsion. But the important thing to remember is that when you are getting trying to get a formula for torsion, you should remember that the curvature should never vanish, okay. The torsion is defined only when the curvature doesn't vanish, okay. So for this, you see, then we also want to try to make sense of torsion as change of a, the change in rate of change of turning angle for torsion, okay. But that is a little bit messy. But to understand why this is a mess is that, we have to first look at this thing that we last saw. Namely, you see, if you take the curve, then you have the so-called tangent direction, unit tangent, okay. Mind you, you are on a curve given by gamma s, okay, and at every point you have the tangent vector. So at every point you have the tangent vector like this, and this is gamma dot of s, okay, and this is written as t cap of s, okay. You have this tangent vector, okay. Then you have the geometric normal, which is it is going to be in the osculating plane, which contains the tangent vector, and this is going to be n hat of s, okay. And these two sit on a plane which is called the oscillating plane. It contains the circle of curvature and the center of curvature, and this is the plane temporarily where the curve is entering and leaving, all right. And then we have the so-called binormal. The binormal is this b hat of s, and this is defined so as to be a unit vector, and so that this t hat, n hat and b hat, or t cap, b cap, t cap, n cap, b cap in that order should be a right-handed system, okay. So what this means is that this angle is 90, this angle is also 90, and so is this angle, okay. So if I draw it more, so what I mean is this angle is also 90, okay. So these are three perpendicular planes, all right. So, and we the idea is that, so therefore this, you see, this b hat is t cap cross b cap is t cap cross n cap, okay. And then if you find the instantaneous rate of change of b cap, okay, that is supposed to measure what? It is supposed to measure the instantaneous rate of change of the binormal, okay. But remember, the binormal is perpendicular to the osculating plane. So the change in the binormal is also going to reflect the change in the osculating plane, and that's supposed to be the torsion, okay. That's what you want to measure. And the big deal is that this change is always occurring in a direction parallel to the principal normal n cap, okay. That's because of this thing that we saw, namely, if you differentiate this by using the product rule, then what happens is that you get, you get this expression that the b cap dot, which is the rate of change of b cap with respect to s, that becomes t cap times n cap dot, okay. And now you see, Therefore, b cap dot is a vector which is perpendicular to both t cap and n cap dot, and there is a unique candidate for that, namely this n cap itself. You see, n cap is perpendicular to t cap by definition because it is a principal normal. Okay, and in fact, remember, n cap was defined using t cap. So, in fact, it was defined using t cap, namely n cap is actually t cap dot of s. Okay, divided by ks, and this was motivated by the corresponding form for the plane curve case. Okay, so so you see n cap is perpendicular to n cap dot also, and that is because n cap is a unit vector. For a unit vector, its derivative is perpendicular to the original unit vector. So therefore, the moral of the story is that this b cap dot has to be in the direction of n cap. So b cap dot is a scalar times n cap, and then that scalar is exactly, we write it as minus tau, and this minus is purposely put there for geometric reasons. Okay, of course, you could have put it as plus tau. There are some books, if you read several books, you will see in some books it's written as plus tau, in some books it's written as minus tau, but this minus tau is more significant. Okay, and geometrically, all right, and therefore, and this tau, whatever it is, that is your torsion. So basically, you see the rate at which b cap changes, which is b cap dot, that change happens in the direction parallel to the normal, the principal normal, and the magnitude of this change is given by mod of tau. Okay, and when you write it as a vector, you have to put this minus sign. That is the convention. Okay, and it has a geometric meaning. So now you see, we would like to just like curvature. See, for example, in the plane curve case, curvature is rate of change of a turning angle, and the turning angle is the angle made by the unit tangent vector with respect to any fixed direction. Okay, and there we can take any fixed direction in the plane, because you see, the turning is happening, the axis of turning is always normal to the plane, and that is constant. Okay, so you see, the turning angle should always be taken in the plane with respect to, you should measure it with respect to a constant vector in the plane. Okay, which is normal to the axis of rotation. Okay, now if you think about it, what is happening in this case is that you see the osculating, what is happening is that the osculating plane is kind of, it is rotating with axis along the parallel to the tangent direction. Okay, that's what this says. So you see, you have the tangent direction like this. If the curve is going like this is the tangent direction, this is the normal direction, this is the binormal. Okay, and the rate of change of the binormal is in the normal direction, it's parallel to the normal direction, so it's in this plane, and this plane is called it's called the normal plane. It contains the binormal and the normal. Mind you, there are three planes involved. There is one plane which is a tangent, which contains the tangent and the principal normal. Okay, that is the osculating plane. Then there is this plane which contains the binormal and the normal. This is the normal plane, and then there is yet another plane which contains the tangent and the binormal. This is the rectifying plane. Okay, so what is happening is that you see, this change in the binormal instantaneously is occurring only in the normal plane, and therefore you should ideally take a turning angle only with respect to a vector, constant vector or unit vector in the normal plane. Okay, so that is very, very important. So therefore, the definition has to be given carefully. If you take psi s to be a turning angle for b cap, okay, it is an angle from a fixed constant non-zero vector to the direction given by the binormal. Okay, then you need to take that in the normal plane. Okay, and then the claim is that the rate of change of that angle, that turning angle, is your torsion. Okay, and why is that true? That is a simple calculation that we can see. So you see, so here is my picture. I have this curve gamma given by gamma of s, capital gamma of s. As usual, you see, s is always the arc length, increasing arc length. Curve is parametrized by increasing arc length, so that it is unit speed curve. Okay, and formally everything is defined only for unit speed curves. Okay, so gamma dot is your t, gamma dot is your t cap, and mind you, gamma dot is length 1 because it's unit speed. So t cap is already unit vector. Okay, then you have this n cap, which is the normal direction. Okay, principal normal, and then you have b cap, which completes the right-handed triad. So b cap is just t cap cross n cap. Okay, now see, there is this plane that I have marked in orange, which is the normal plane. It contains the normal and the binormal. Okay, in this plane I am taking a vector v naught. Okay, and I am measuring the angle that b, the binormal b hat makes with this v naught, and calling that angle as psi s. Okay, then the claim is that d psi s by ds is nothing but the torsion. So that is the statement. So the torsion is the rate of change of this turning angle. Okay, and the proof of this is quite straightforward. Namely, you compute how do you measure this angle by, so the cosine of psi of s is going to be b hat of s dot v naught. Okay, and then I have to put by norm v naught. I have to do this. Okay, and if you assume that norm v naught is 1, okay, that is v naught vector is the same as v naught cap. Okay, it's a unit vector. Then cos psi s is going to be just cos of psi of s. Okay, is going to be just b cap s dot v naught cap. All right, and but now you see what is you differentiate this, because you see I want to relate to torsion. Torsion is what I have to differentiate the binormal. And we just now got it here. The way we have defined torsion is you differentiate the binormal, and that is in the n cap direction, and the scalar involved is minus t. So b cap dot is equal to minus tau n cap. Okay, therefore you differentiate it. If you do d by ds, mind you, the dot is derivative with respect to s. If you do that, you will get minus sine psi of s d psi of s by ds is equal to, here if I differentiate, this is a constant vector, and here I will get b cap dot of s dot v naught cap. Okay, but now you use this formula here, so the right side will become so I will have minus sine psi of s d psi of s by ds is equal to, on this side I'll just plug this in. I'll get minus tau of s n hat of s dot v naught cap. Okay, and now if you what is the angle between n hat and v naught? You see there is an extra 90 degrees. Okay, so it's 90 plus, so this is going to be minus tau of s. Okay, this n hat dot, the dot product is norm of this, norm of that. The norms are all 1, so I'll just get the cosine of the angle between these two, and that is 90 plus I'm going to get psi of s. Okay, and then I should end up with what happens if I do it like this. The sign issue comes because you see the sign should be adjusted in such a way that for a right-handed helix the torsion must be positive. Okay, so there is a thumb rule of how to give the sign to the torsion, and that's basically if you want the right hand thumb rule. If you have a right-handed screw moving like this, then the motion should be like this. So it's the so-called right hand thumb rule. Okay, and that, so a right-handed helix is one which moves like that. Okay, so the sign should be adjusted properly so that this is accommodated. You have to take care to measure only the positive angle. All right, but the way, so you can see what I have done is the angle I have measured is in the negative direction. Is it not? Yeah, on the plane with respect to the tangent direction, this direction is clockwise. Okay, so that's the problem. So let us do the following thing. So let us put the let us put the vector like this. Okay, and call this vector like this, and So let us do this, because you have to be careful about the way. See, you have see, when the turning angle comes, you also need to record the increase or decrease in the turning angle. That means it's not just the magnitude of the turning angle that is important, you also need its sign. So that means you must prescribe a sense for the turning angle, and the sense for the turning angle should be, the anticlockwise sense with respect to the unit tangent as the normal to the normal plane. Okay, so you see this angle. See, I'll take this as psi of s. Okay, if I do it like this, then what happens is that I am going to, and I go through this. So I will get, of course, cos psi s. That's not a problem. It will be the dot product divided by the norm, and if you take the norm as 1, it's just going to be the dot product. And then because I want to use this, that the derivative of the binormal is what gives the torsion. So I have to differentiate this. If I differentiate it, I get this. Okay, and then at this point, this becomes, then things are nice. I mean, now it is actually the angle between n hat s and v naught. Oops, the now it works out correctly. So you see, the sense of the angle is extremely important. Okay, the sense in which you are measuring the angle. So now the angle between n hat s and v naught is 90 minus psi s, this angle. Okay, so here it will become cos of 90 minus psi of s, and so now everything is fine. So you get minus sin psi s d psi s by ds is equal to minus tau of s sine of psi of s, and this sin psi s and this minus go away, and then you will get d psi s by ds is equal to tau of s. So you see it. So you have to be very careful with the sense in which you are measuring the angle. Okay, and it's very, very clear on the normal plane, the angle from the fixed vector v naught, which you have taken as unit vector, the sense in which you should measure it should be the anticlockwise sense with respect to the normal going out as the normal from the binormal plane going out as a tangent direction. Okay, and of course the problem with this kind of a definition is that I am only this unit vector is only fixed in the binormal plane at that point. If I change the point, the unit vector, the binormal plane will change. Everything will change. The osculating plane will change. The rectifying plane, the normal plane, everything will change. Okay. Therefore, this choice of vector will also change. Okay. So this is a comparison only at one point. Okay. That constant vector is chosen only to compare what happens to the change in the binormal at that point. Okay. So the important thing you are using is that if you change the arc length slightly, the change in the binormal is just wiggling along the normal plane, and that is what this computation says, that b cap dot is in the n direction. Okay, or opposite to the n direction. It's parallel to the n direction. Okay, so in that sense, this is an interpretation of torsion, but actually there are more deeper interpretations of torsion. There is also what is called an osculating sphere, which involves a radius of torsion. Okay, so all these things can be made sense of. Okay, there is a more deeper theory. All right, but let's not get into that at this point. Okay, you have a question? No, so V naught, yeah, this is a good question. See, this V naught is a kind of fixed normal vector in it's a fixed vector in the normal plane at that point. And then you are moving the point, but this V naught is not changed. Okay, and of course, there will be a little change in the normal plane. There will be a little change in the osculating plane. Okay, and all that, but the way you have to infinitesimally interpret this b cap dot is equal to minus tau n is that essentially there is no change in the normal direction, and the infinitesimal change is happening only in the normal direction, parallel to the normal direction at that point. Okay, so this is a instantaneous interpretation of this. Okay, so this v naught is you change the arc length, in principle, the normal plane also changes. All the planes change. Okay, but then this V naught cap is fixed only on the normal plane at that S value. Okay, and then you are varying S slightly. The big deal is how even if you vary S slightly, okay, the rotation of B cap is instantaneously happening only in the N cap direction and with an axis parallel to the T cap direction. Okay, that is the interpretation. Okay, so there is in fact there is one more deeper interpretation where you can have both the the rotational movement of B head along with the translational movement along the tangent direction, and this is a kind of screw motion of a rigid body. Okay, and then it is a very deep theorem that any instantaneous motion of a rigid body looks like this. Okay, so there are more theorems in mechanics that relate to this. Okay, but we are looking at only the rotational part of it. All right, so this is just to say that there is some semblance of turning angle for torsion. Okay, now what I want to do is, of course, this is not very, it's not very attractive. It's not as attractive as the turning angle for the plane curve case for a tangent, because there the turning angle was with respect to a fixed vector. The turning angle for a plane curve is the angle made with a fixed direction by the tangent direction, the unit tangent. Okay, and that fixed direction, why you could choose that fixed direction once and for all for all points on the curve, that was because there it was a plane curve. The normal direction, the binormal is constant. Therefore, everything is happening, the turning is happening only on the plane. Okay, and the axis of rotation is always in the binormal is always normal to the plane, and that is constant. So you could choose one direction for every point on the curve, but in the three-dimensional case, you cannot do that. At every point, dynamically, the binormal is changing, the normal plane itself is changing. So you have to carefully choose at every point. Given a point, you have to choose a vector only in the normal plane at that point. Okay, and you have to do this comparison only with respect to a constant unit vector there. Okay, so this is kind of in a way it is not as satisfying, but it gives you an idea that there is some sense of a turning angle. Okay, there is no one fixed vector. So this is an instant. So that's what I'm saying. So as the point moves on the curve, the normal planes are also changing. Therefore, this choice of a constant vector, unit vector in the normal plane, okay, ideally in between the binormal and the normal, principal normal, such as V naught cap, that also depends on the point. You have to choose one such for every point, okay, and work with it. The other way is that you think that you are in the Frenet-Serret frame fixed, okay, and you keep a single V naught there, but now you are moving along with V naught. Okay, so if your frame of reference is you are sitting on the curve, okay, then this V naught can be taken fixed. Okay, so it is a relativistic point of view. If you think of, if you are observing from outside the curve, the Frenet-Serret frame is moving. Okay, but if you are sitting on the curve and you fix the Frenet-Serret frame as your frame, then what is happening is that your motion is curving in space. Okay, and it's the usual coordinates which will be turning around. Okay, so it's a relativistic way of looking like that. If you look at it like that, then you could have fixed a single unit vector in the normal plane. Okay, and then of course everything will depend on your motion. Okay, so that is also another way of thinking of it. Okay, so anyway, so what I want to do is now to do is that there are two important things I want to do. One is to get the Frenet-Serret differential equations. The other thing I want to do is get a formula for torsion which works for any parametrization. Okay, so what is the Frenet-Serret differential equation? For space curves. So as I told you, the differential equation records the change of the frame, and the change of the frame is the rate of change of the three orthonormal vectors in the frame, unit vectors in the frame. So it's t cap of s, b cap, t cap, n cap, and b cap in that order. Okay, and this is a frame, and I want to look at the change of this. So what you have to do is you have to do d by ds of this, and this is so the d by ds is a dot. So I'll get t cap dot of s, n cap dot of s, and b cap dot of s. The question is, what is this equal to? So here's the differential equation. Mind you, t cap dot, n cap dot, b cap dot are 3 vectors, and they are also they can also be resolved in terms of t cap, n cap, b cap, because t cap, n cap, b cap is already a orthonormal frame. Okay, you can, any vector in 3 space can be resolved in terms of 3 linearly independent vectors, and in this case you are having 3 mutually orthogonal vectors. Mutually orthogonal vectors are linearly independent. Okay, and in fact they are even unit vectors. So in this case, what you will get? You will get this very nice thing. You will get 0 ks, 0 minus ks, sorry, minus, so here I will get minus of ks 0. Okay, so you see this matrix is the same matrix in the curve case. Okay, then and it's a skew symmetric 2 by 2 matrix. Okay, and in the space curve case also it's the same, except the torsion is going to come. So what you will get is, here you will get tau s, and here you are going to get minus tau s. Okay, and you are going to get a 0. There's a 0. There's a 0. And on this side, I will get t cap, n cap, b cap. Okay. So this is the Frenet-Serret differential equation. All right. So if you write it out as 3 differential equations, what you will get is t cap dot is equal to, you see, if you do vector multiplication, I mean matrix multiplication, this matrix acting on that vector on the right side, you will get k s times n cap. Okay, then you will get n cap, and n cap dot of s is equal to minus k of s t cap plus tau of s b cap. Okay, so let me put an s carefully. Okay, and the third vector will be b cap dot of s is equal to minus tau of s n cap dot of s, n cap of s. Okay, so these are the 3 equations. Out of these 3, you see, this was the starting point. See, the first equation, why is it true? That is the definition of n cap. So it is true by the definition of n cap, because n cap was defined as 1 by ks t cap dot. Okay, then this one we derived, we just showed that, the rate of change of the binormal is in parallel to the normal direction, and the scalar involved is negative of the torsion. Okay, so this we have just shown that. So the only thing that you have to show is this, the fellow in the middle. This is the guy that needs to be shown. That is, you need to show that n cap, its derivative is partially in the tangent direction and partially in the binormal direction. Okay, so how do you do that? So you see, you want n cap dot of s, this is d by ds of n cap of s, but now use the fact that you see t cap, n cap, b cap are a right-handed triad. So you have, if you draw a picture, this is t cap, then you have perpendicular to that you have n cap, and then perpendicular to that you have b cap. Okay, and they are all, so everything is 90 degrees. Okay, so from this you can write n cap in terms of t cap and b cap, and what is that? If you do b cap, so n cap will be just b cap cross t cap. Okay, right? Have I written it correctly? I cross j, so b cross t is n, so that's correct. That's correct. Okay, fine. So you have to be careful about that. So n cap is this, so it just differentiate it. So this is just d by ds of b cap cross t cap. Okay, b cap of s cross t cap of s. So you will get now use product rule. So d by ds of b cap of s cross t cap of s. Okay, plus b cap of s cross d by ds of t cap of s, okay. And but you see, this is if you look at it, we already have formula. So this is what? This is just b cap dot s cross t cap s plus b cap s cross t cap dot of s, okay. But we have already the formulas for, b cap dot and t cap dot here. So just plug them in. So you see, this b cap dot is minus tau n cap. So this is minus tau of s n cap of s, okay, cross t cap of s plus here I will get b cap of s cross what is t cap dot. T cap dot is from the first equation. It is ks n cap. So cross k of s n cap of s, okay. And now you see, so you will get minus tau of s times n cap of s cross t cap of s, okay, plus remove the scalar out, k of s times b cap of s cross n cap of s, okay. Again, look at this triad. You see, n cross t, okay. N cross t is what is this? N cross t is going to be minus b, right? And b cross n is going to be plus tau, plus t cap, okay, plus t. So this is minus b cap, and this is n cross t n cross t is minus b, right? And b cross n is what? B cross n is minus t. So you should get so minus ks t cap of s plus tau of s b cap of s. So this is the thing that we wanted. So what was it on the left side? You have, okay. So it's minus k t plus tau b, okay, which is this equation. Okay, so that proves the Frenet-Serret differential equations. Okay, so again, just to remind you, the Frenet-Serret differential equations, what they give is, they give the dynamics of a kinematics of a particle moving on the curve, and the curve is simply a solution of this matrix differential equation. Or you can think of it as three first order simultaneous first order differential equations. Okay, fine. So that is this. The next thing we want to do is to get hold of a formula for calculating the torsion for a curve which is not necessarily unit speed parametrized. Okay, so and we derived such a formula, for the curvature case. You have to grapple with just calculus, just derivatives. Okay, you are given a regular curve, small gamma of t, okay, and it's not necessarily unit speed, okay, and you also assume that the curvature is not zero, okay. Then you want to compute the torsion, and you want to do it everything in terms of this parameter t, which is only a regular parameter, is not necessarily unit speed parameter, okay. So so this is the situation that we are in. We have so let me write this formula for tau for a curve tau of t, for a curve gamma of t regular with the curvature never zero. Curvature never zero. Okay, so so the important thing is need not be unit speed parametrized. Okay, so this is a very, very important thing, and you already recall that how did we do this? you first took, everything is defined only first using unit speed parameterization. Even the curvature, how is it defined? It is the magnitude of the acceleration vector after you take a unit speed parameterization of the curve. And the unit speed reparameterization of a regular curve always exists. And it is kind of unique. The only change of variable you will have to do is you have to do the parameterization with respect to arc length, plus or minus the arc length plus a constant. We already seen that. So you see, therefore, what is the usual thing that we do? We have some open interval a, b, and you have this gamma t going to gamma t, and this gamma is going into R3. Mind you, it's now a space curve, and there is gamma dot of t is never 0. It's never the 0 vector. This is the same as saying that it's the speed, which is norm gamma dot of t is never 0. Okay, and this is regular. This is a regular parameterization. Okay, and what is the unit speed parameterization? What you do is you do it like this. You have this c comma d. Okay, and you have a change of variable. You send u to some g of u, which is your t. Okay, and this is your change of variable, so that this new curve capital gamma, which is gamma of u, this is unit speed. Okay, and we know how to do this. Basically, what you have to do is that there is this g comes with this inverse g inverse. Okay, and the g inverse map will take t to g inverse of t, which is u, and this u is nothing but arc length s. So u is just s. Okay, which is u is just s, which is s of t. Okay, and the point is, gamma of s of t is your small gamma of t. Okay, so this is the important thing. All right, and recall that the curvature at t is given by, this is the magnitude of the curvature is given by norm gamma dot of t cross gamma double dot of t by norm gamma dot of t the whole cube. Okay, we have already seen this, right? We derived this. Now the claim is the following: the torsion is given by the following formula. The scalar triple product gamma dot, gamma double dot, gamma. So let me put a t also. It's a scalar triple product gamma dot of t, gamma double dot of t, gamma triple dot of t divided by norm gamma dot of t cross gamma double dot of t whole square. This is the formula for the torsion. Okay, and of course, the fellow on the top is scalar triple product. You can write it variously as gamma dot of t cross gamma double dot of t dot gamma triple dot t. You can write it like this. Okay, and you can interchange the dot and the cross also. Okay, and wherever you put a cross, you have to bracket that, because that's a vector. Okay, and the dot is between one vector and another. Okay, so the point is that you must understand why you need this condition that the curvature never vanishes. You see, because you see the curvature non-vanishing. First of all, to define the curvature, you see in the denominator there is this norm gamma dot, and for that norm gamma dot should never vanish. That's regularity for you. Without regularity, you cannot define curvature. And you see in the numerator of curvature, you have this norm gamma dot cross gamma double dot, and that you see occurs in the denominator of the torsion to the second power. So if the curvature is 0, then the numerator norm of gamma dot cross gamma double dot, that has to be 0. Okay, and if that is 0, then this denominator will become 0, and then torsion is not defined. So you see, for defining torsion, you also need that the curvature is not 0, and whatever is occurring in the numerator of the curvature formula is in the second power occurring in the denominator of the torsion formula. You must notice that mathematically. Okay, now it's a matter of calculation, just calculus. So let us do this. And of course, this formula is welcome because now, finding a unit speed parameterization is not so easy. Okay, because finding the unit speed parameterization involves, finding this u, but this u is, so u is, so I have to, so this u is s of t, that is fine, but writing it like this is very deceptive. It's deceptive because this is what you use for calculations and this is easy, but actually what you are given is only this small gamma. Okay, from small gamma, if you want capital gamma, you have to write the other way of doing it, which is, you see, you have to take small gamma and you see, you have to write this g of u. Okay, then small, if you write t equal to g of u, then this is your gamma of u. Okay, and therefore, the big deal is that you want to find this change of, you have to find this function g, which is the change. Okay, but this g is, s is actually g inverse, so g is s inverse. So though it is easy to find s, it's hard to find s inverse. You have to invert the arc length. That is your u. That is your g. Okay, so the problem is that in general, finding the unit speed parameterization is not easy. Okay, because it amounts to finding g, and g is s inverse. Okay, so whereas this is quite straightforward to write, and this is what we will use for making the calculations. Okay, so you have to remember that. So it's impractical to find the unit speed parameterization. So for any parameterization, you want a formula, and that's this formula here. It's as useful as this formula is for curvature. All right, now how do you get this formula? So what you do is that you use the definition. So proof of the claim is, it's just a exercise in calculus. So you see, we have already, we have the following thing. What is the definition of the torsion? So b cap dot is equal to minus tau n cap. Okay, by the definition of torsion. So if you want this tau, you dot both sides with n cap, you will get b cap dot n cap is equal to minus tau n cap dot n cap, and this is of course 1. So you will get tau is equal to minus b cap dot n cap. Okay, so this is what you have to compute. All right, now but you see, what is b cap dot? B cap dot is, d by ds. Okay, mind you, here everything, the dot here is d by ds. Okay, and whenever you write these kind of things, you should remember that you are using the unit speed parameterization. Okay, and that means you are doing this for capital gamma, which is the unit speed parameterization. So to be very careful, what I will do is, I will just, if you want, you can put a gamma here. Okay, and you can be very careful, but I'll be not so serious about it. Okay, but it is there at the back. You should remember that. Okay, so you see b cap. So that's the reason when I write b cap dot, it's with respect to d by ds. So this is what? This is by definition d by ds of what am I going to get? I'm going to get now what is b? So it is d by ds of b cap. But what is b cap? B cap is t cap dot cross n cap. That is the by definition. Okay, and then you apply the product rule. So you will get d by ds t cap cross n cap plus t cap cross d by ds of n cap. Okay, and so I will get so this d by ds of t cap is going to be t cap dot cross n cap plus t cap cross n cap dot. Okay, and therefore if you bring this here, you will get tau is equal to minus, I have to substitute this guy, which is this guy. So I'll get minus of t t cap dot cross n cap plus t cap cross n cap dot, okay, that is this term, and then I have to bring in this n here, I have to dot this with n cap, okay, and you can see immediately that this will give me 0. That's because it's a scalar triple product, any two, if any two vectors are parallel in a scalar triple product, you are going to get 0, because actually it records the signed, volume of the parallelepiped given by these three vectors. And if any two are parallel, then it's going to be, it's no longer a three-dimensional thing. Okay, so it will have 0 volume. Okay, so essentially this is going to be minus, you see, n cap dot, or let me write it in that order, it doesn't matter, minus t cap cross n cap dot n cap. Okay, this is my tau. Okay, so this is the working formula I have to compute. Okay, so what do I have to do? I have to compute this t cap. Okay, then I have to compute this n cap dot. Then I have to compute this n cap also. Okay, I have to compute all of these fellows. Now remember, all this is happening with respect to capital gamma. Mind you, all these relations that you write involving Frenet-Serret and the Frenet-Serret frame, okay, all these things are only for the unit speed curve. So is very, very important that you have to write. So I should say here, this whole thing is valid only for capital gamma of S. Okay, so all the things that are happening is for capital gamma. What you have to do is you have to translate it to small gamma of t. Okay, and for that what you have to use is that that is where you have to use this fact that you see capital gamma of S of t is small gamma of t. So you need to translate to the variable t and gamma of t, and the fact that you will use is capital gamma of S of t is small gamma of t. This is what you use. All right, so you have to compute all these fellows here in terms of small gamma and small t. Okay, and how do you do that? So let's start by computing what is n hat. So n hat is actually n hat of S. If you want, it is n hat of capital gamma of S. Okay, remember, and you see this now this how was this n hat defined? It is the first Frenet-Serret relation, and that was the way in which n hat was defined. The inspiration was from the plane curve case. Okay, note that Frenet-Serret n hat of S is defined as 1 by k of S into t cap dot of S. Okay, so you have to use this expression, and this expression is in S. You have to convert it into an expression in small t and small gamma. Okay, and it's a calculus computation. Okay, and so maybe I should continue in the next class. So this is it's long to write, but it is very easy. Okay, you just do it mechanically. You do it. Okay, there is finally I'll tell you there's going to be some huge crocodile-like term going to come up. Okay, in the cross product, but you should never expand it. You cleverly notice that everything gets killed except for 2-3 terms. You just put them together, you get the answer. Okay, lots of scalar triple products will just disappear because 2 vectors are parallel. So you should never expand it and just observe, and you will get the final formula. So you can try it out for yourself. Anyway, I will do it in the next class. Okay, so I'll stop here.